Hello and welcome to the question show. Your questions, Paul's answers. Once again, every week I gather up all of your questions and answer them in this question show. But this week I've got a special guest answer, my good friend Dr. Paul Matt Sutter. We're here on the Sea and Stars cruise in the middle of the Caribbean Ocean, somewhere off the coast of Florida, and I picked a bunch of the hardest questions I could find to unleash them on my good friend Paul here. Now, the other cool thing about this is we're in front of a live audience. So for those of you who wanted to join us on the cruise, sorry you missed it, but before we get started, Paul, there's another adventure that we're going to be doing in March.
Yeah, March, you and me are going to Costa Rica for a stargazing jungle extravaganza. There's volcanoes, there's the aforementioned jungles, there are hanging zipline stuff, and then stargazing every night.
Yeah, so if you're interested in that, go check out astrotours.co and go down to I forget the name of the Costa Rican one.
The Wild Skies of Costa Rica.
There you go. We're going to bring cool telescopes, show you the night sky, and check out all of these cool adventures in Costa Rica with you. So it's going to be a lot of fun. I've been to Costa Rica before. I really like the place, and I would love for you to be able to join us. And I think we've still got some slots available. So,
Yep.
So join us. All right, let's get into the questions.
I am scared and excited.
All right. So Animus Australis asks, a fundamental question came to my mind. What is space itself? Imagine a perfect vacuum, space with no particles at all. What is it? Does it have any properties on its own? Are there any concepts or models describing all this emptiness?
Wow, that is a really fun question. And the most fun questions are when there are different answers depending on which field of physics you ask. So if you ask in relativity, in general and special relativity, space itself is a set of points. It's a way for us to mark events. It's a bunch of coordinates. And in general relativity, those coordinates themselves are alive. The distances between points can shrink or expand or bend, and that is our experience of gravity. But if you ask in, say, quantum field theory, the vacuum of space itself, the fundamental space-time of our reality, is actually buzzing. It's alive with effervescent virtual particles that are constantly popping in and out of existence. And these two pictures don't quite agree with each other, and that's part of the mystery of modern physics.
And so to even ask that question, what is space without stuff? And I think the questioner is asking, like, if you removed all the planets and the stars and the moons and the galaxies and the particles of hydrogen and the rocks and all that, all of the dark matter. Yep. If you removed all of that, you would still be left with this, as you said, this effervescent, these virtual particles that are appearing out of that. Right. They are intrinsic to the property of space itself.
Exactly. In this picture of quantum field theory, space itself, empty space, the pure vacuum, has an energy associated with that. The energy is not zero. It's something else. We're all sitting on top of a sea of energy, just like the ship sits on top of a sea of ocean. There's this fundamental property of the vacuum.
All My Lettuce asks, let's say we figure out how to create negative mass. If we were to put negative mass into a stellar mass black hole until it doesn't have enough mass to be a black hole, what would it turn into? A neutron star? An explosion?
Something. Yeah, exactly. Negative mass. This is a wonderful thing. As far as we can tell, first off, negative mass does not exist in our universe. And it's thought experiments like this that allow us to reason why negative mass would not exist in our universe. For one thing, it would start maybe blowing up black holes. Like, how does a ball of mass that weighs negative 10 kilograms, how does that behave in space-time? We could figure that out. What would happen if we tossed into a black hole? We could figure that out. The black hole would probably lose mass, but then that ball also has energy. It's complicated, doesn't it? Negative mass, if it were to exist in our universe, would do all sorts of counterintuitive things. Like, if you take negative mass and positive mass next to each other, they would just spontaneously start moving, and they would accelerate as fast as they can without any force applied to them, which violates everything we know about momentum and inertia. And if you were to toss a negative 10-kilogram ball into a black hole, the black hole would probably shrink by a little bit, which kind of violates everything we know about black holes.
So we say there's nothing you can do to destroy a black hole except for just waiting it out.
Wait.
But if you could generate negative mass and you could feed it into a black hole, you could make a black hole disappear, but also violate all the laws of physics as we understand them.
Yeah, there is that.
Right. Brett Rylan asks, "Hi Fraser, I watched one of Paul Sutter's latest Ask a Spaceman videos just before this one, and one of the comments he made during the video was that as an object falling into a black hole is seen by an observer to slow down and become redshifted as it approaches the event horizon, but is never observed to cross that horizon. However, we recently observed the gravitational waves of two black holes merging. Isn't this a contradiction?" Now first, before I get into the question, I'm glad I've got Paul here to answer questions for Paul, but it's funny to me that people will ask on my channel to...
Probably because my response, I think I remember this question, is, that's great, it's on my list to answer in the future. And then it takes about a year and a half for me to get to that.
And so they knew that I could give a pipeline right to Paul to get it answered right away.
Special access, cheat code.
Cheat code. Someone just used the cheat code. So Paul, can you explain first that idea of the black holes falling into the event horizon, and then why this might not be a contradiction?
Yeah, so the event horizon of a black hole is a very special place. If you're falling into a black hole, you just cruise on through space. There's no line, there's no beacons, there's no feeling, food still tastes the same. Everything's the same outside and inside of an event horizon for you. But what the event horizon marks is what outside observers get to see. So an outside observer watching you fall into the black hole doesn't ever actually see you cross that boundary. You just get redder and redder and redder as your light coming off you has to struggle against all that extreme gravity to reach the observer's eyeballs. You get slower and slower and slower from time dilation. Now, that's one scenario. That's its own scenario of a black hole sitting there minding its own business with one thing falling into it. Two black holes merging together is a different scenario. It's a different problem. It's a different homework problem. It's the physics of dynamic black holes that are growing or shrinking or merging, orbiting around each other, have a different set of intuitions associated with them than the traditional story of a black hole sitting by itself with something falling into it. So in the case of two black holes falling into each other, the rules of the game are now different. You're using a different set of equations to describe their behavior. And the gravitational waves are emitted not from the centers of the black holes, they're emitted from just outside the surface. These are massive structures completely warping space-time around them, and as they move, then anything just outside the black hole gets affected. Like another nautical metaphor, like a ship moving through the water creates waves, it creates wakes. These are effects on the outside of the surface.
Jeremy Harris asks, "Hi, I was thinking about your comments regarding the cosmic microwave background. Would there have been a time in the past as the universe expanded where imaginary observers would have seen the entire universe as visible light, changing hue over eons through the spectrum from violet through to red before it disappeared into the infrared range?"
Yeah, great question. So cosmic microwave background, this baby picture of the universe that was released when our universe was just 380,000 years old, when it went through this very important epoch where it went from very, very hot and dense, cooled down just enough so that atoms could form, and then release some radiation. That radiation has been traveling the cosmos ever since until it hits our detectors and our antennas, and we observe it surrounding us on all sides, this image of an infant universe. When this happened, when the cosmic microwave background first was released, it had a temperature somewhere around this temperature of the surface of our sun. It was literally white hot radiation. If you were standing inside that universe, it would be like standing on the surface of the sun. It had a temperature of 10,000 Kelvin, plus or minus. And very quickly, as the universe expanded, this radiation thinned out and it cooled down, it redshifted and redshifted. So yeah, it would start out white hot, and within, say, 100,000 years, you would see it shift down to reds, and then another million years down to the infrared, and then all the way down is the microwave where it is today.
But the shifting that we see, like, it would be cooling down, but it would also be red shifting away because of its motion away from us.
Right. So the temperature of the black body radiation that is the cosmic microwave background goes down to the 4th power of the size of the universe. So if the universe doubles in radius, then the temperature drops by a factor of 16.
Right.
So very, very, very quick.
Right. But would it be like the sun is giving off photons of many different colors? Would the cosmic microwave have that same kind of variation? So some radio, some gamma radiation, but mainly that temperature that you mentioned.
Oh yeah, absolutely. So this cosmic microwave background emits as what's called a black body, which is just the radiation given off by hot things. And you're right, it's all different frequencies, peaking in one particular range depending on its temperature, but a little bit of hotter stuff, a little bit of cooler stuff. In fact, the cosmic microwave background is the most perfect black body known to humanity. It is far more perfect of a black body than anything we can make in any laboratory. So in the early days, yeah, there were gamma rays, there were X-rays, and over time, the whole thing just shifts down and down and down.
Custly Bane asks, are there binary galaxies?
You know, we see galaxies doing all sorts of crazy stuff. Some galaxies are alone. Most galaxies have a bunch of dwarf galaxies in orbit around them. Some galaxies are crashing together, and we do see some examples of galaxies that appear to be orbiting around each other, that something that we would call a binary. This is a very rare scenario, however, and it is not a very stable situation. So I would hesitate to call it a binary orbiting pair, except we see, some movement like this. Eventually they're either going to crash into each other or move on. So they're not like stable over 10 billion years.
And is that because with, say, 2 planets or 2 stars, they have more gravity that's holding them into their own respective spheres, and you're not getting the tidal forces trying to mess them up, while with galaxies, the tidal forces are more dominant in that encounter?
Yeah, exactly. There's a lot of tidal forces between interacting galaxies. Galaxies have all sorts of crazy movements. It's not like inside a galaxy where everything's squished on a plane. So when we observe the motions of galaxies, it's like a beehive inside of clusters. They're moving all sorts of places. It's very hard to get captures like that.
Kiana Brajon, do you think there could be a celestial body at L3? So not necessarily a counter-Earth, but I don't know, asteroid Pluto sized. So just to give people a bit of a background, the L3, that's the Lagrange point 3. L1 is the in-between, say, the two objects. So Sun and Earth, you've got the in-between the Earth and the Sun. L2 is on the other side of the Sun. L3 is on the other side of the Earth. And L4 and L5 are leading and trailing us in our orbit around the Sun. So could you have something stable, a Pluto out there at L3?
I don't remember exactly off the top of my head. I don't think L3 is stable. It's not. Well, there you go. L3 is not. It is a point in space where the gravitational forces are in balance, but it's not a stable point where the gravitational forces are in balance. So if you put something there, it's like trying to balance a pencil on its tip. It's stable as long as nobody moves or breathes on it or does anything at all. And as soon as there's a slight perturbation, a slight knock, the whole thing comes crashing down.
It's easy to maintain its position with fuel.
Right.
The way we described it at the top of a mountain.
Yeah,
it's going to roll down the top of a mountain. With the L4 and the L5, those are stable. So could you put a Pluto-sized object into, say, the L4 or the L5, which are stable?
Pluto-sized object might be a little bit extreme. Here on the following and trailing in our orbit around the sun. So these Lagrange points are based on the mathematics done by a French physicist, Lagrange, who was studying a very particular problem where you have one big thing, a smaller thing, and then are there any places where you can sprinkle dust, tiny stuff, things like asteroids. If you start putting a big object there, like Pluto is kind of big, then like the question with black holes, that's a new problem. That's a new set of math, because now you have the interactions between the sun, the Earth, and your new thing. If your new thing is small enough that you can basically ignore its gravitational influence, then you can put it there. But as long as if it gets too big, then it starts wanting to be a player in the game, right, and you won't necessarily be stable. I think Pluto might be too big.
So as long as the mass of that object is insignificant compared to the mass of the sun and the Earth, then
you're golden.
Then you're golden.
These rules apply.
Right, and the second it becomes too massive, then it throws the whole thing out of whack.
Do new set of math, and you might be stable, but probably isn't.
Ollie the monkey. Hey Fraser, I was wondering, do we experience any time dilation due to the velocity and rotation of the Earth, Solar System, Milky Way? And if we do, would we age faster if, say, the Milky Way was stationary in space?
That's really cool. So if you add up all of our motion, the rotation of the Earth, the orbit of the Earth around the Sun, the orbit of the Sun around the galactic center, our motion of the Milky Way to Andromeda, our whole motion towards the Great Attractor, it adds up to something like 600 kilometers per second relative to the cosmic microwave background, this shell of radiation that surrounds us on all sides. And that's pretty fast for people. It's also super slow compared to the speed of light. So yes, there is time dilation in that, but really not enough to matter.
How fast do you need to be going for time dilation to start having an effect?
The general ballpark of if you want to enter it into the relativistic regime, if you really want to start caring about these special relativity effects, usually somewhere around at least 10% of the speed of light. And usually it's not really up until you're at 90% where you can start counting on it.
Right. So you can do much faster.
Much faster.
Nasser M. Could dark matter be explained by a percentage of planets in the galaxy being completely surrounded by Dyson spheres?
Hey, no, we'll go there. This was not exactly Dyson Spheres, but this was one of the main contenders when we first began seeing dark matter, that there is an invisible component to our universe. When you look at a galaxy and you see all the hot glowy stuff, that's not all there is to a galaxy. There's more stuff. So what could it be? Maybe it's normal stuff. It's protons and neutrons and Dyson spheres, but all made out of all our normal stuff, but just really dark. It's not glowing, it's not reflecting much, and so it's really hard to see. But we have very, very strong limits from our knowledge of the extremely early universe. When in the extremely early universe, when our universe was 10 minutes old, that's when it was fusing all of the protons, all of the hydrogen, all of the helium, and a little bit of lithium that we see today. And you can ask, of that early universe, how many protons can you make? How much hydrogen, how much helium can you manufacture in the early universe? You can go out and test that, because we understand nuclear physics really well, and we can make predictions for the ratios of hydrogen and helium and different kinds of lithium and how much light is out there and all this. And we get the predictions right, so we feel pretty confident in this answer. And that tells us the maximum amount of normal matter there is. And there just isn't enough stuff, enough raw building material to make dark matter be just very dim but normal matter. It has to be something else.
Norman Hairston. When two black holes combine, substantial angular momentum must be present. Does that angular momentum remain in the combined black hole, or is it somehow dissipated?
That's a really good question. This is actually a really tough problem. When two black holes are orbiting far away from each other, they're doing this nice lazy orbits, they are emitting gravitational radiation, but incredibly weak. And they're slowly over time, slinking down close to each other, and then it gets really frenetic, and they combine. This transition, as far as we can tell in the mathematics, takes like 10 billion years to go the final light year. Like if you have two black holes orbiting each other by a light year and they eventually collapse, as far as we can tell, that's supposed to take 10 billion years. But black holes merge way more often than that. So something has to happen to speed that up, to bleed off that angular momentum so they actually can get in close. Once they get close, then they're emitting so much gravitational radiation that is what's pulling off all that angular momentum. That's where it's dumping all that energy, all that momentum. And then in the final black hole, that thing is spinning like a madhouse. It has tons of angular momentum that it slowly loses over time. So getting the black holes close is an unsolved problem in physics. Once they're close, it's all gravitational radiation.
Terry Fitzsimmons. If nothing can escape a black hole, even light, then what are the jets of stuff that gets ejected out of the poles when they start gobbling matter up? How does that material escape from the black hole?
Yeah, and I this is a great question, and I'm not surprised that they asked this question, because when we're describing what happens to matter as it falls into a black hole and the formation of these jets, it's really tempting to get poetic about it and say like, oh, these jets escaping from the surface and blasting out tens of thousands of light years.
It's almost sometimes
I'm
come in
mocking
one
myself here.
Yeah, it'll come in one sentence. You'll say, a black hole is a place where nothing, not even light, can escape. And we see black holes because they're bright, shining radiation. And there's literally in one sentence, you've contradicted yourself.
So here's what's going on with these jets as they eat. That material doesn't cross the event horizon. It falls in and falls and forms an accretion disk around that black hole. And then in that scenario, crazy stuff happens to that gas. The magnetic fields go incredibly strong. There are beams of radiation. There are electric fields that are governing the behavior. And some material does fall in to that event horizon and is never seen again. But a good fraction of that material instead gets wrapped up in the magnetic fields, instead flies along that surface of the event horizon, winds itself up, and then gets ejected. So this material escapes the vicinity of the black hole, but doesn't escape the black hole itself. If you fall through that event horizon, you are done.
Rob67. Question. Could the growing cosmic expansion be explained by the gravity of other universes pulling with their mass onto our universe's matter?
One of the hardest things to wrap your head around, anyone's head, including mine, when it comes to the expansion of the universe, is how our universe is completely self-contained, or can be completely self-contained. So galaxies are getting further away from each other over time, on average. Our universe is expanding. There is no edge. There is no outside. There is nothing for the universe to expand into. That concept doesn't even make sense. You can just write down simple equations, relatively simple equations, that describe this behavior. It's all self-contained. The evolution of our universe is governed totally by the interior contents of our universe. There is a connection there between the contents and the evolution. There could be multiverses, there could be all sorts of crazy stuff, higher dimensions, all that, but you don't need them. You can 100% describe our universe using our universe.
But one of the things that I have heard is that, for example, one of the explanations for why gravity might be weaker compared to the other forces is that maybe it's bleeding in from some other...
Maybe there is more spatial dimensions on macroscopic scales. You can have that. So it's not ruled out. And they are invoked to explain some things we don't understand about the universe, but just the vanilla Big Bang stuff, expansion of the universe, dark energy, all that, you just need our normal self-contained four-dimensional universe.
Well, Paul, we did it.
We did it. That's it.
Yeah, those are my questions. Those are the zingers that
Those
I brought.
are awesome questions.
That I, well,
Wonderful
absolutely,
questions.
and that's why I saved them up for someone with a PhD in astrophysics
making stuff up.
and making stuff up. Now, Paul, tell people where they can find out more about what you do.
You can go to my website, pmsutter.com. It has links to everything I do, to my Ask a Spaceman videos, my podcast, Space Radio, the art and science collaborations I do, to the Astrotours, which we're on right now. Everything I do in my newsletter comes from pmsutter.com.
All right, and we'll put a link to your YouTube channel
Appreciate it.
here, and next week I'll be back in my frozen Canadian North in the forest again, just as you've come to expect. So again, keep those questions coming. I love them. Thanks everyone, and thanks to our live audience here on the cruise ship. Woo! And we'll see you next week.